Hi everyone. This lecture is again on continuation with our discussion on the Fourier transforms. In the previous lecture, in two lectures, we introduced the idea of energy, power, and we also discussed what Fourier transform is. In this lecture, we will look at a few more properties and we will discuss how to interpret the Fourier transforms and what inference we can get and how does one plot something called spectrum, or rather, energy and power spectral density of a signal. Okay, so what we discussed in the previous lecture is about energy and power. In this lecture, we will see how that energy and power is distributed as a function of frequency. Okay, and that is a very important a very important idea for the design of RF systems. So I'll continue with where we left off in the previous lecture. So I was talking about energy and power. I said they are not unique. Different signals can have same energy and same power, but it's a very important metric to characterize a signal. Okay, but Fourier transform, on the other hand, we said you are converting x of t into a different signal x of f, and that's a unique transformation. Every signal will have a unique Fourier transform. Okay, no two different signals will have the same Fourier transform. It's that uniqueness property that helps us in synthesizing the signal back from the knowledge of the Fourier transform. Okay, so that's a very important property we discussed. So today I'll start with one very important point, which is a very important property which we didn't explicitly mention in the previous lecture, called absolute integrability. We can define Fourier transform for those signals for which this integral will converge. So you take your signal, take absolute value of it and integrate it over all time, that integral value should converge. But if you see, we defined Fourier transforms for cos omega naught t. We defined Fourier transforms for cos omega naught t, and we can readily see, and we also defined for A. A is a constant DC signal. Both these signals will not obey this integral. They are not absolutely integrable. You integrate a constant signal from infinity to dt, you will get infinity here. Similarly, you take mod of cos of t. Not just a cos t will integrate to 0, but if you take modulus of cos of t, that will integrate to a finite, in fact, to a much larger value. And if you integrate it for all time, this will also blow up to infinity. So for power signals, we can't define Fourier transforms. But then we did define in the previous lecture, that is with the help of impulses. Okay, we took the help of impulses, and then we defined Fourier transform using impulses. For example, sinusoid. A sinusoid is a signal of single frequency. Okay, it's a signal of single frequency, and we said Fourier representation is representing a signal as a bunch of sinusoids added together. But since it's a single frequency, you just need one frequency to represent it. You don't need a continuum or infinite frequencies. But the Fourier transform graph, that's why will contain an impulse, because it has just energy at one frequency and nowhere else. Okay, so that's the thing about power signals. Power signals, by definition, by the general definition and rules of Fourier transform, we can't define Fourier transform for them, but we do mathematically define it using impulses. If you compute in MATLAB, you always truncate the sine waves. You truncate the sine waves and then compute it, so they are not really power signals. Okay, so just to give you an idea, we'll probably talk about more about this in an assignment. I'll give you an assignment and try to compute, ask you to compute FFT Fourier transforms, and you'll understand better. Now, I discussed one important property. I said if you shift in time domain, if you have a signal delta of t whose Fourier transform is 1, and if I shift the signal in time domain by say t seconds, then the Fourier transform gets multiplied by a factor of e power minus j 2 pi ft. So this function delta of t minus t in time domain, it's called as a delay function. Okay, so if you pass a signal through a transfer function whose impulse response is delta of t minus t, your output signal is going to be a delayed version. And in frequency domain, if you look at it, it's going to be a complex exponential. Okay, now what I'll do is I'll do, and I mean, I'll take another delayed version, which is delta of t plus t. Then that Fourier transform is going to be e power plus j 2 pi ft. And I'll take the average of the two. I'll add these two and take an average. So that's what I've written here. This signal here is delta of t minus t, which I've written in this equation here. T minus t, there is an impulse here with a magnitude of half. So when I write half here, it's not impulse magnitude, but it's impulse weight. If you integrate the impulse, the value of this integral will be half. So we normally, for an impulse function, we write the weight of the impulse as its amplitude. Because if you see, ideally impulse blows up to infinity. At that instant, uh, wherever there is an impulse, the value just, it's much higher. It's very close to a very large number or very close to infinity. But when we write half here, it's just the weight of the impulse function or the integral value of it. If you integrate an impulse, this is the value you're going to get. So that's what we have written here. In frequency domain, that's going to be a cosine, cos of 2 pi ft. So because if you add these two in frequency domain, and in frequency domain, the Fourier transform of this signal, which is delta of t plus delta of t minus t plus t by 2, in frequency domain, that Fourier transform is going to be, this is f here, ft plus, I'm writing it here, so e power plus j 2 pi ft by 2. And that's nothing but cos of 2 pi ft. You see a very interesting result here. We have previously analyzed cosines and found that the Fourier domain contained impulses. Now, if I have impulses in time domain, which are symmetric around the origin, for a real signal, let's assume they are even as well, then in frequency domain, it will be a periodic signal. It's a very interesting property. So if you have impulses in time, then there will be periodicity in frequency domain. If you look at the frequency domain, the spectrum has periodicity. Okay, so this is one interesting property. What we saw previously was, if you have a sinusoid, a cos omega naught t, in time domain, if you have a sinusoid, in frequency domain, we saw two impulses at minus omega naught or minus f naught and plus f naught, where f naught here is omega naught by 2 pi. You will have two impulses. Now, we can also argue this from duality property. If I have impulses in time domain, then I should expect a sinusoid, a periodic signal in frequency domain. So your Fourier transform will be periodic if you have impulses in time domain. That's a very interesting property. It's one of the foundations for digital signal processing. If you see most signals, once you sample it, their spectrum is going to look periodic. So we'll talk about this later when we talk about sampling in ADCs. But right now, I just wanted to introduce it as a property of Fourier transform. If you have impulses in one domain, you should expect periodicity in the other domain, in frequency domain. Okay. Now we'll look at the Fourier transform of another interesting function, which is the unit step function. I will not derive this result, but I'll explain you the result intuitively. Why does this result, the Fourier transform result for step function, make sense? And also, we will see the knowledge of step function, the Fourier transform of the step function, helps us in deriving the Fourier transform of a very interesting filter called Hilbert filter. Okay, which is a very important thing when we talk about amplitude modulation. It is very helpful in shaping the spectrum of a signal to a desired shape. So to introduce that Hilbert filter, I'm teaching what Fourier transform of a step function. Now we have already discussed, if you take a constant DC signal, a DC signal with unit amplitude, if the amplitude of the DC signal is constant, then the Fourier transform is an impulse. Okay, so a DC signal can be seen as a sinusoid of zero frequency. So if you take a cos omega naught t, if you make omega naught tend to 0, then that will be like a DC signal. So therefore, it is also a sinusoid of zero frequency. So you will end up seeing impulses in frequency domain. You will see an impulse at f equal to 0. Okay, and we know that the Fourier transform is delta of f. Now, before I discuss this Fourier transform of a step function, if you see a step function, it's a function which is continuous for all time except at t equal to 0. At t equal to 0, it has a discontinuity. There is a step discontinuity of unit magnitude. So which means you can't precisely describe what is the value at t equal to 0. So when we define Fourier transform, we assume that it is defined for continuous functions, functions whose values don't exhibit any discontinuity. But this step function has a step discontinuity at one point in time. Okay, so then how do we define Fourier transform for this? So there is a very interesting theorem. Again, this is from Fourier series. What happens is that the Fourier series for such functions, if the discontinuity is finite, if this discontinuity is a small discontinuity and a finite discontinuity, then the Fourier transform will converge to point. If you synthesize, if you see once, what is the goal of Fourier transform? Once you have Fourier transform, you should be able to synthesize your signal back from the knowledge of the Fourier transform. Okay, so you should be able to, at every point in time, x of t, if I write the synthesis equation, what am I doing here? I'm trying to compute this integral e power j 2 pi f t df. So this is the synthesis integral. At every point in time, for every value of t, I will evaluate this integral and find out what will be the value of that integral. It should converge at every point. Okay, so but if there is a discontinuity, then what value will this integral converge to? And that there is a very interesting theorem which shows that it will converge to the average of these two values. Wherever there is a discontinuity, for example, if there is a discontinuity at x equal to 0, it will converge to x of 0 minus plus x of 0 plus by 2. It will converge to the average of the two values. So whenever you have a discontinuity at any point, the Fourier transform will converge to the average of these two values. Now, if you look at this function, this is it's a continuous function. A constant DC function is a continuous function. There is no discontinuity, so we didn't have to worry about that. So Fourier transform was 0 everywhere except at origin, and we could describe its Fourier transform using an impulse, even though this function is not absolutely integrable. But now, if you know the Fourier transform, I'll derive the Fourier transform of u of t using the knowledge that u of t can be seen as an integral of a step function, an impulse function. If you integrate an impulse function, you will get a step function. We know the Fourier transform of an impulse function is 1, right? So Fourier transform of an impulse function is 1. And there is another interesting property of Fourier transforms, which is, if you, sorry, I don't have space here. Let me just write it here. So if you have a signal x of t, whose Fourier transform is x of f, the Fourier transform of integral of x of t, this is given by x of f upon j 2 pi f. Okay, so this is an expression. There are some additional terms as well, which will depend upon discontinuity and all that. I'll right now I'll not talk about it. Let's just use this result alone. This result is valid if the average value of your function x of t is 0. Okay, if the average value of x of t is 0, this is a very valid result. For step function, I mean, for an impulse function, that doesn't hold true, but we will use this expression. So since we know this impulse response of a step function is, the Fourier transform of an impulse function is 1, the Fourier transform of a step function will be 1 by j 2 pi f. But now we have to look at a step function and see if it satisfies all the criterion. Will this integral, I mean, is this fine? I mean, is this a complete Fourier transform of a step function? The answer is no, because if you, a very interesting property of Fourier transform is, what is the value at x of t? Let's look at the synthesis equation. If you see a synthesis equation, it is integral x of f df into e, there is a e power plus j 2 pi ft dt df. This is your synthesis equation. What is the value at x of 0? X of 0 is simply integral minus infinity to plus infinity x of f df. So the average, if you compute the overall integration of your Fourier transform, that will give me the value of x of t at t equal to 0. It has to give me the value at t equal to 0. But if I integrate this function, integral 1 by j 2 pi f over all interval plus to minus infinity over df, what do you think will be the value of this integral? Can you think of what will be the value of this integral? See, remember, this is an odd function. 1 by j 2 pi f is an odd function. So if I'm integrating, and it's a symmetric around origin, if you take its magnitude, it has odd symmetry. So what will be the value of this integral? So it's a function that's going to look like this 0, right? So if you look at this function, it's going to look like what I'm plotting 1 by j 2 pi f. It's going to look like this. So if I integrate this integral will exactly cancel out with this integral. Okay, this will be 1 by j and this will be minus 1 by j. Okay, so for negative frequencies, it will be the area and these two areas will cancel out and you will get 0. But we said for Fourier transform, it has to converge to half. It should give me half. So that's why we know the Fourier transform for a constant function. For a constant function, it is delta of f. But for a step function, because at origin it has to converge to half, we will add this extra factor delta of by 2. So this extra factor delta f by 2 comes because at t equal to 0, if you take a conventional DC function, it has to converge to delta ff, 1. If you integrate it, if I add delta ff to this, then if I integrate it at origin, I'm going to get a plus half, I'll get half. Okay, so that's why this extra delta f by 2 comes here in this equation. So the Fourier transform of a step function will be 1 by j 2 pi f plus delta f by 2, and it makes intuitive sense. This we understood, it comes from an impulse. Integrate an impulse, you get the first part. The second part is also intuitive because Fourier transform converges to the average of the two values at the discontinuity. So that's why you get delta of f by 2. So this is a result which we will use it to compute the Fourier transform of a Hilbert filter. So that's why I discussed this result. There are mathematical ways of deriving this and proving this, but let's not worry about that. If you understood this much, that's more than sufficient. Okay, we just need to have an intuitive understanding and should be able to use it in our analysis. That's it. Now we will compute the Fourier transform of u of minus t. If x of t has a Fourier transform of x of f, x of minus t, we can very easily show we'll have a Fourier transform of x of minus f. So substitute f equal to minus f, you will get minus of 1 by j 2 pi f. The second term will be delta of minus f by 2. And I had discussed another result in the previous lecture, which I said you can prove it yourself very easily. Delta of at is given by 1 by mod a into delta of t. Okay, impulse function can be seen as an even function. So delta of minus f by 2 can be written as delta f plus f by 2. So the Fourier transform of this term can be written as delta f by 2. Now we'll try to compute the Fourier transform of a signum function. A signum function is a function that looks like this. At t equal to t less than 0, it will look like a negative step function of value minus 1. At t greater than 0, it will look like a positive step function of value plus 1. And at t equal to 0, there is a discontinuity. So what do you think will be the value the Fourier transform should converge to? At t equal to 0, the Fourier transform will converge to what value? 0, right? So it will converge to 0. That's it. So you shouldn't expect to see some weird things in the Fourier transform expression the way we see for step function. So if you see the signum function, I'll construct a signum function using u of t minus u of minus t. Okay, u of t minus u of minus t will give me a signum function. This is u of t here, and this is u of minus t with a minus sign. Add the two functions, you will get the signum function. So I'm going to subtract this minus this in time domain. So Fourier transforms will also get subtracted. So this term minus this term, you will get 1 by the 2 term will go away. You will get 2 by j 2 pi f. So you get 1 by j pi f and delta of f will cancel out. And you're left with a simple expression like this, 1 by j pi f. Okay, so you get the Fourier transform of a signum function, a sine of t is 1 by j pi f. Fine. Now if you see here, if you integrate this function for all frequencies, minus infinity to plus infinity, 1 by j pi f df, you will get this to be 0. Okay, you will get the integral to be 0. And that makes sense because signum anyways converges to 0. So we are fine there. Now from the knowledge of the duality property, we know that if x of t has a Fourier transform of x of f, x of t, capital X of t, will have a Fourier transform of small x of minus f. So 1 by j pi t, I just replaced it here, 1 by j pi t will have a Fourier transform of signum of minus f, right? I've just put t as minus t here, so t as minus f. So you'll get signum of minus f. And this is how signum of minus f will look like. So signum of f is a positive function. Just reflect it around the origin. You will get a function that looks like this. Okay, so I'll multiply on both sides by j. If you, because Fourier transform is a linear transformation, so if you multiply your signal by x of t, Fourier transform also gets multiplied by the same factor. So if I multiply on both sides by j, I will end up getting 1 by pi t. The Fourier transform of the function 1 by 5 pi t will be j signum of minus f. Or I can simply see the signum function, if you see, is an odd function. Since signum function is an odd function, signum of minus f can be written as minus of signum of f. It's an odd function. So you can see around origin, it exhibits odd symmetry. So x of t is minus of x of minus t. So it's an odd function. So I'll replace it with minus of signum of f. So what you get here is minus j signum of f. So that's the Fourier transform of 1 by pi t. And this transfer function in frequency domain is a very interesting function. All positive frequencies, this function minus j signum of f in time domain 1 by pi t looks like this. It's a hyperbolic function. Okay. But in frequency domain, the Fourier transform is all positive frequencies will undergo a constant phase shift of pi by 2. Right? It's minus j. They will all undergo a phase shift of pi by 2. And therefore, this function, in time domain, this function 1 by pi t is called a Hilbert filter or a pi by 2 phase shifter. This comes in very useful, it comes in very handy when we are generating single sideband signals. Okay, if you want to generate a single sideband signal, you need to have a filter with a characteristic 1 by pi t. Okay, which was very popular in AM radios. So we will talk about that when we discuss AM and FM modulation schemes in the next lectures. That's it. So this is what I wanted to discuss. The Fourier transform of the function 1 by pi t, which is this function 1 by pi t, is also called a Hilbert filter. The Fourier transform is minus of j signum of f. We also refer to it as a pi by 2 phase shifter. Okay, so that's about Fourier transforms. So we have discussed I have discussed most of the properties of Fourier transforms which are important for this course. Right now, we are going to look at another very interesting idea, which is the spectrum, the density spectrum. So far, we discussed energy, we discussed power, and we discussed Fourier transform. But what exactly does Fourier transform convey to us? That is the question we will try to answer in this part of the lecture. Now, energy tells you that we said it's a very important characteristic of a signal. Fourier transform tells you in frequency how that energy is distributed as a function of frequency. So before I go about that, I'll just discuss one interesting property called orthogonality property, which again, it's a consequence which I have not explicitly mentioned, but since it's a graduate course, most of you would have gone through an undergraduate course. If you have two signals x1 of t and x2 of t, in time domain, if you multiply the two signals, the Fourier transform of the two signals is given by convolution of the two signals. In frequency domain, they undergo convolution. Similarly, if you convolve in time domain, from duality, I can argue that if I convolve two signals, x1 of t convolved with x2 of t, the Fourier transform is simply the product of the two Fourier transforms, x1 of f into x2 of f. Using this property, this convolution property, or the second one, this property is called multiplication property or modulation property. Okay, using these two properties, you can show a very simple result, which is the integral of x1 of t into x2 of t into dt. So this is nothing but the inner product of two real signals. I've taken two real signals x1 and x2, and I'm computing their inner product. Okay, I'm projecting x1 onto x2 and seeing what will be that integral. That integral we discussed in time domain in the previous lecture. Now I'm trying to show that it can be expressed in terms of Fourier transforms as well. It will be integral of x1 of f into x2 of minus f df. This result can be very easily proven using these two properties. It's a very trivial result to prove. But what you need to note here is that the test for orthogonality, if you want to know if two signals are orthogonal, then we can show that the product of this should be 0. I mean, the integral of the product of the two signals should be 0. This is valid for real signals. I'll stick to that. Probably, later I'll discuss for complex signals. You can study it later. And I'll give it as an assignment. If you take the product of two real signals and integrate it, if it goes to zero, then we know the two signals are orthogonal. Now, the test for orthogonality can also be carried out in frequency domain. You can also carry it out in frequency domain. You can just take its product, the Fourier transform product, and see what happens to that integral. So that's a very important consequence of this properties of Fourier transforms. Now, if you look at time domain, even when you visually look at two signals, you can say if they're orthogonal or not. Now let's look at these two signals. These two are pulse signals. In time domain, they two are pulse signals, but they are separated in time. They are separated in time. There is no overlap at all. So if I directly compute the product of these two signals, what will be the product? It will be zero for all time, right? Since it's non-overlapping, I compute the product, it's going to be zero for all time. So I can directly say that these two signals are orthogonal. Now, if you look at two sinusoids, I think, we are more used to sinusoids. Let's say we take two sinusoids of different frequencies. So let's say I construct another sinusoid, which is say twice the frequency. Okay, so it's a sinusoid. I probably haven't drawn it to scale here, but it's a signal. Let's say this signal frequency is f naught. This signal's frequency is 2f naught. In Fourier domain, in frequency domain, the Fourier transform, the first sine wave is going to look, it's going to have an impulse at f naught and minus f naught. The second sine wave is going to have impulse at 2f naught and minus 2f naught. So if you see, in frequency domain, they are separated. They don't overlap. In time domain, they are overlapping. Okay, in time domain, if you see both the signals are overlapping, you have to calculate the integral and then show that it is zero. But if you look at its Fourier transform, you can directly see that there is no overlap. So you take the product of the two Fourier transforms, you're going to get zero again. So therefore, it's a very useful tool. I mean, you can, if you with the knowledge of Fourier transform, you can also predict orthogonality of two signals by just by inspecting their Fourier transforms. Okay, so that's a very useful property here. So I've shown you the Fourier transforms of two signals. Are these two signals orthogonal? You see here that the Fourier transforms are not overlapping. So directly you can say that they are orthogonal just by visual inspection of the Fourier transform. Okay, so these are the intuitions I just want you to understand. So it will be very easy if you understood all this to follow the next the course material we'll discuss later. We also discussed in the previous lectures a very interesting theorem called Parseval's theorem. We said if you compute the energy of a signal mod of x of t the whole square dt, energy of a signal, using this equation, see, the energy of a signal is given by x of t multiplied by x conjugate of t, and then you integrate it over all time, and this turns out to be mod of x of t the whole square dt. Now, using this integral, I can easily show that the energy will be mod of x of f the whole square df. I can readily show the Fourier transform of x of t. The Fourier transform of x of t is x of f. The Fourier transform of x conjugate of t. So again, this is a useful property. I probably have a result here. Yeah, I'll discuss that later. But the Fourier transform of x conjugate of t. If let's say you conjugate a signal, the Fourier transform is given by x conjugate of minus f. Okay, for a real signal, what is x conjugate of minus f? For a real signal, x conjugate of minus f is x of f itself, right? That's one of the first properties of Fourier transform. X conjugate of minus f is also x of f. So for a real signal, x conjugate of t is also x of t. So now you see the result makes sense. If you assume a real signal, I just want to show that for a complex signal, x conjugate of t will have a Fourier transform of x conjugate of minus f. Using these two results, we can very trivially show this result. So this is what we call the Parseval's theorem. To compute the energy of a signal, you don't need to compute the energy in free time domain. With the knowledge of Fourier transform, also you can compute its energy. Okay, you take your Fourier transform, take its magnitude square and integrate it, you will get the energy. So that's what this equation is telling us. You don't need to compute it in time domain explicitly, but you can also do it in frequency domain. So this equation is conveying a very interesting information. So if you take x of f the whole square and integrate it or for all time, for all frequency, then I get the total energy of a signal. So what information do you think x of f square contains? So you have a function. If you integrate it, you are getting energy. Okay. So the function x of square, x of f the whole square, conveys the energy density. So that is the energy per unit frequency. So it tells you how energy is distributed as a function of frequency. For example, most of you have done basic probability and statistics. So in probability, we are used to the term called probability density function. Let's assume a uniformly distributed probability density function. So 0 to 1 with a weight of 1. So this is a uniformly distributed random variable with a density function given by this. Now, if I ask you what is the probability, what is the probability that your value of x lies between a certain interval, let's say 0 to half. How do you do that? You just calculate the integral, you integrate the density function from 0 to half and give me the probability out. In the same way, with the knowledge of x of f the whole square, you can actually tell me, if I ask you what is the energy contained in the signal in a small band of frequencies, in a small band of frequencies delta f, then all you need to do is just integrate this. Let's assume delta f is so small, then it will be just the area under the integral will be just a area under this rectangle, which is delta f the whole square into uh, mod of x of f the whole square into delta f. So this is the energy contained in the frequency band delta f. So what x of f the whole square conveys is E of delta f upon delta f. So this is the energy per unit frequency. So this mod of x of f the whole square for a real signal and an energy signal for which the energy is finite, if you square the Fourier transform, that in what it conveys is this distribution of energy as a function of frequency. Right? It tells you, if you integrate this equation, it tells you the whole energy. But if you look at the Fourier transform and the content, mod of x of f the whole square conveys the information of how that energy is distributed. For example, in a narrow band RF system, if let's say if you have a signal, typically we will try to uh, do some. I mean, let's say this is a narrow band. We will later discuss a word called FDMA systems. So where information is conveyed is present only in a narrow range of frequencies for an intended receiver. So by looking at spectrum, power spectrum or energy spectral density, you will immediately know this is a narrow band system. And if you want to receive this band, then you have to design some appropriate filter which will only receive your intended message. Okay, that information, how your energy is distributed, that is conveyed by the energy spectral density. Okay, that's why the Fourier transform, when you square it, it not only conveys, it not only helps you in finding energy or inferring a lot of information in which probably may not be obvious in time. It can also be used for testing orthogonality and so on. It mainly tells you the distribution of that energy over frequencies, and that's the most important property for us. I'll just introduce another idea because since I told you it's a quick refresher, like kind of a lecture where I'm just quickly refreshing what you have done in your undergraduate. Another very important function, it's called the autocorrelation function. We said previously we defined an integral called inner product, where we took two signals, x1 of t, x2 of t, and computed their product. And said this integral, when you compute it, it can tell us if two signals are orthogonal or not. Okay, I'm projecting one signal onto the other signal and seeing if they're orthogonal or not. So this integral tells you a measure of closeness. So I said I'm using the word closeness. It's because when you see the theory of signal space, you can represent signal as a vector. So we can use all the terminologies that we use for vector spaces for signals as well. So we can say whether these two signals are, how closely related are these two signals. That information will be conveyed by this integral. We don't need to compare two different signals, but what if I try to compute inner product of a signal with itself? That integral will become autocorrelation function. So you take a signal x of t, delay it by tau seconds, and then compute the inner product. This integral is what we call the autocorrelation function. You are correlating the signal with itself. But remember, it's not the signal itself, but a delayed version of the signal. A delayed version of the signal. Okay, this will give you a lot of information. Autocorrelation function gives you a lot of information. It will tell you if two signals, if let's say the delayed version of the signal has no correlation with the signal itself, then the integral will converge to zero. So you will know that, okay, even if I delay the signal a little bit, it's uncorrelated. This is a very important property for noise signals or random signals. Okay, so that's why I just introduced the definition now. We will revisit this in a slightly different way when we talk about noise. So, if you we can make an interesting observation. We are used to this thing called the convolution integral. If I convolve two signals, x1 of t into x2 of t, if you look at this autocorrelation function integral, that resembles a convolution integral. Now let's look at a simple convolution integral here. If you convolve two signals, x1 of t into x2 of t, the convolution is given by x1 of tau into x2 of t minus tau d tau. Okay, this is the convolution integral. Now compare this with the convolution integral. Compare this with the compare this with the convolution integral. What I'll do is here, I think for a proper comparison, I'll just replace tau with t. I'll just replace tau with t and t with tau. So what you will get, x1 of t into x2 of tau minus t. It's just a variable, so I'm just replacing tau with t and t with tau. So I get x1 of t into x2 of tau minus t dt. Now compare this equation to this equation. You can immediately see there is a similarity between the two equations. x1 of t here is x of t. x2 of t here is x star of t. Is it x2 of t? But here if you see the difference here is tau minus t. Here you have t minus tau. And you can very easily show it is actually x star of minus t, x conjugate of minus t. So your autocorrelation function Rx of tau or Rx of t can be written as convolution of x of t into x conjugate of minus t. Okay. Now I'll take Fourier transform on both the sides and we'll see what happens if I take Fourier transform of the autocorrelation function. What you get is a Fourier transform of this function. Since we know convolution translates to multiplication in frequency domain, the Fourier transform of x of t is x of f. The Fourier transform of x conjugate of minus t. X conjugate of minus t, you can, again, this is something we can readily show. X conjugate of minus t will have a Fourier transform of x conjugate of f. So here I've written three results. I'll just take you through just a minute, and even if you can take this, that is sufficient. But I'll just take it, spend a minute on it. If x of t has a Fourier transform of x of f, x conjugate of t has a Fourier transform of x conjugate of minus f. Okay, so x conjugate of minus t, because if you take any function and just invert your time, so make time as minus t, in frequency domain, the Fourier transform will become minus f. So it will become x conjugate of f. So substituting it here, you will end up getting x of f into x conjugate of f. So the product of these two will be mod of x of f the whole square. So this term mod of x of f the whole square is what we call energy spectral density previously. So you can compute energy spectral density by computing the Fourier transform of the autocorrelation function. So you're taking a function, delaying it, and then computing, see how well it is correlated with itself for different delays. And that function which you are computing for different delays, that function Rx of tau is called autocorrelation function. It will not only tell you about the correlation for different time shifts, but if you take its Fourier transform, it gives you the information of the energy spectral density. It tells you the distribution of energy as a function of frequency. So this function Sx of f for an energy signal, this is true for an energy signal, the Fourier transform of an autocorrelation function gives the energy spectral density itself. I'll take an example, and you will see how simple it is. But for power signals, unfortunately, this integral will not converge. See, for example, if you compute this integral for any power signal, let's say I make tau equal to 0. If I make tau equal to 0 and compute this integral, it will become infinity for a DC signal. If let's take a DC signal, a real DC signal, this integral will blow up to infinity. So in those cases, if you have a power signal, then we define what we call a time averaged autocorrelation function. You compute the autocorrelation function as it is, okay, but define a time average. So the same way we did for power and energy, right? So we did the same thing. The only difference here is it is x star of t minus tau. There is a variable. We are changing tau and computing this. So can you tell me, by looking at this equation, what will be Rx of 0? Let's say tau is 0. If tau is 0, what will this term give me? We have discussed all the previous definitions before. Limit of t naught tending to 0, 1 by t naught, integral minus t naught by t naught, mod of x of t the whole square dt. What is that?
Power signal.
The power itself, right? So that's the power of a signal itself. So that's another interesting property. If you take the autocorrelation function and compute its value at the origin for a power signal, you will get the power of the signal itself at Rx of 0. Similarly, for an energy signal, Rx of 0 will convey the energy of the signal. Next thing, again, this is a result. I'll leave it aside, but I'll write the code, the final result. Now, if you take the Fourier transform of a time averaged autocorrelation function, if you take the Fourier transform of a time averaged, or this is called a time averaged autocorrelation function, if you take its Fourier transform, what you will end up getting is a power spectral density. It's the distribution of power as a function of frequency. Okay. For energy signals, we have ESD, which is energy spectral density. So you compute autocorrelation function and take it for a transform, you get energy spectral density. For a power signal, you can compute time average autocorrelation functions because autocorrelation function will not converge. And if you compute its power spectrum for a transform, what you will get here is the power spectral density Sx of f. So this, the notations keep changing. So Sxx of f, because it's autocorrelation, you correlate with the signal with itself. So it's called Sxx of f. But oftentimes we remove that x and represent it as just s. That whatever the signal is, capital X of f represents it's a uh, it's a spectral density. Okay. So here this Sx of f is a power spectral density. So we'll take an example and you will see immediately how it works very simply. So let's say we have a signal A cos omega naught t. We know the Fourier transform is, Fourier transform for this signal is delta of f minus f naught a by 2 and delta of f plus f naught a by 2. So you will have, you need two complex exponentials. This is actually a complex exponential in time domain. This is another complex exponential in time domain. The average of the two, add the two complex exponentials and you will get a sinusoid. So the amplitudes is a by 2 and a by 2. This is the Fourier transform. Now let's compute its autocorrelation function. So I'll use, this is a power signal, so I'll have to compute time averaged autocorrelation function. So integrate it and a cos omega naught t into a cos omega naught into t minus tau. If you do that, I'll get the a square term separately. So you have cos a cos b. So cos a plus b plus cos a minus b. So you will get a minus b will be cos of omega naught tau plus cos of 2 omega naught t minus omega naught tau dt. Integrate it over time dt. You have to integrate it over dt from minus t naught by 2 to plus t naught by 2. So what will be this integral? Let's assume t naught is a very large number. What will be the value of this integral? This is just a sinusoid in time. If you integrate it, this will converge to 0. This omega tau for different values of tau is just a constant phase. So if you integrate a sinusoid over many cycles, you will get 0. Okay, full cycles, if you integrate it, you will get 0. This term, there is a half factor, I missed it out here. Cos a plus b is one half of cos a plus b plus cos a minus b. So I'll get a term a square by 2 here, and this term will converge to a square by 2 into cos omega naught tau into t naught, and when you divide it by t naught, the t naught goes away. What you get here is a square by 2 into cos omega naught tau. What I've gotten, if I computed time averaged autocorrelation function, I've gotten the same cosine sinusoid, but now with an amplitude of a square by 2. And you can immediately see, if I make tau as 0, Rx of 0 is a square by 2, that will give me the power of the signal. It will immediately give me the power of the signal. Now if you compute its Fourier transform, the Fourier transform of the autocorrelation function, I'll just take a few minutes and finish it. Just give me a few minutes, I'll finish it. If you compute its Fourier transform, you will get a square by 4, so half of this. So this can be written as e power j omega naught tau plus e power minus j omega naught tau by 2. So you will get a square by 4 into delta of f minus f naught, a square by 4 into delta of f plus f naught. And if you plot this function, this is how your power spectral density looks like. So this function is called the power spectral density for a sinusoid. And you see here, half the power is on the positive frequencies, half the power is on the negative frequencies. You add the two powers because it's impulses, you can directly add the powers. The total power is a square by 2. So if you take a sinusoid, and if you can compute Fourier transforms on MATLAB, you'll notice that half the power will be on the positive frequencies, half of it will be on the negative frequencies. You add the two, you will get a square by 2. Integrate this function in frequency domain, you will get the power of the signal as well. Okay, so that's this Fourier transform of a sine wave. Now, if you take x of t as sine omega naught t, I've just shifted it by sine omega naught t, you can very easily show the autocorrelation function is same. It is same as the as it was for cos omega naught t. It is a square by 2 into cos omega naught t. Now you can immediately see I've defined autocorrelation function as x of t convolved with x of x conjugate of minus t. Let's assume it's a real signal. For a real signal, then it can be written as x of t convolved with x of minus t. X of minus t. So now let's call it Rx of t. If I want to see Rx of minus t, if I want to compute Rx of minus t, I'll make this as minus t and this as plus t, which again converges to the convolution, the same autocorrelation function. So Rx of minus t will be equal to Rx of plus t, which means your autocorrelation function is an even function. If you have a real signal, if your signal x of t is real, autocorrelation is also a real signal and also it is an even function. So if autocorrelation function is a real and even signal, what can you say about its Fourier transform, which is Sx of f, which is the power spectral density? Your power spectral density is also real and even. That follows directly from the properties of Fourier transform. If Rx of tau is real and even, okay, so even x of t can be odd or anything, it doesn't matter. X of t, if it's a real signal, if x of t is a real signal, Rx with autocorrelation function is real and even. So that's why even though we started with a sine omega t, it's an odd function, we will eventually get this. You can very easily do this integral. You will get this expression a square by 2 cos omega naught tau. Okay, so you will have a product term like this, sine into sine. So that will be cos a minus b minus cos a plus b by 2. So that's where you get the cosine term. Okay, so you get this, and the power spectral density will look exactly the same for both sine wave, for a sine and a cos omega naught t. Okay, and the power spectrum density will also have half power on the positive, half power on the negative frequencies. So that's it. So now we have an idea about how to compute Fourier transforms. We have discussed autocorrelation functions. We also saw the advantages and applications of Fourier transforms very briefly. Okay, and we discussed energy spectral density and power spectral density. These tell you how the energy and power are distributed as a function of frequency. And that's very important for RF system designers because that will dictate your center frequency and all of that. Okay, it's very important. And so in the next lecture, I'll start with discussion on the modulation schemes. Thank you.